Hello and welcome. In this video, we are going to analyze an open steady system, a simple tube through which moist air is flowing and is heated. The inlet conditions are supplied and the volume flow rate of the moist air is given to us. The pressure remains constant and we are asked to find, and the exit temperature is given 40 degrees Celsius, and we are asked to find the heat transfer and the relative humidity at the exit. Well, what remains constant along the flow? Of course, one thing is given, pressure remains unchanged, 100 kPa. And then we understand also that because it's simple heating, m dot dry air must be constant at 1 and m dot dry air at 2 must be not changing. Also, we are not taking any vapor out or in, therefore the vapor flow rate is also constant. Their ratio is, of course, omega 1 and omega 2. In other words, theoretically, omega remains constant. So you could either use this and this or this. Any two of these equations will suffice to close the problem. Okay, so let's go launch a suitable test step. Obviously, it's an open steady problem. We follow the specific branch and go to HVAC psychrometry and launch the app. Moist air is already the default fluid and the pressure is initialized to 101 kPa, which is very close to 100 kPa. We could go and split hair here, but it will not change the answer much. The temperature is 10 degrees Celsius. This is the initial inlet condition. Relative humidity is given as 90% and volume flow rate is given as 100 meter cube per minute. It's already meter cube per minute is the default unit. So state 1 is completely determined. For state 2, the temperature is given to us as 40 degrees Celsius. And as we discussed already, the mass flow rate of dry air is not going to change. M dot air 1 and mass flow rate of vapor is not going to change because no vapor, no H2O or dry air is taken out or added in this problem during the flow. So that closes the problem. So we know that omega 2 should be equal to omega 1, 6.854. You can see that it's 6.854 as we expected. You can see the plot on the psychrometric chart. We go from state 1 to state 2 horizontally because this is the omega axis. So we have all the answers that we need in this problem in state 2 really. So first question was find the relative humidity. Notice how dry the air is compared to the inlet state. It was 90% relative humidity and after heating it became about 15% relative humidity. To evaluate the heat transfer, we go to the device panel and it looks a complicated system, but really it's not. We have only one inlet and one exit. State 1 is our inlet and let's say we say state 2 is our exit, and let's leave the other two states blocked. So one inlet and one exit, moisture coming in, going out. We know there is no work transfer and the rest is very simple. The energy equation is now solved because we know all the properties to figure out what is heat transfer, and 62.7, here you go, is our answer. The heat transfer, suppose we had resistance heating. In that case, Q dot will be 0 and W dot external could be found. And of course, that will be negative, but the amount will be identical, 62.7 kilowatt of heating or negative 62.7 kilowatt of electrical work transfer.